Most people think the AI revolution is about software. They imagine new chatbots, powerful algorithms, and ever smarter digital assistants. But behind every AI breakthrough is something much larger and far more physical. AI does not run on ideas alone. It runs on electricity, water, transmission lines, cooling systems, batteries, and industrial infrastructure. The next phase of artificial intelligence may not be determined by who writes the best code. It may be determined by who can build and secure the energy systems required to power intelligence at unprecedented scale. Look closely at what is happening around the world. Massive AI data centers are being constructed at record speed. Companies are investing hundreds of billions of dollars into compute infrastructure. But every new AI model requires more electricity, more cooling, more hardware, and more supporting systems than the generation before it. That means AI is no longer just a software story. It is becoming an infrastructure story. The hidden systems behind AI include nuclear power plants delivering reliable baseload electricity, solar and wind farms generating renewable energy, battery storage systems balancing fluctuations, water treatment facilities providing cooling, transmission grids moving electricity across long distances, and data centers converting that energy into intelligence. Even future technologies such as space-based solar power are now entering conversations about long-term energy security. The real question is no longer how powerful AI can become. The question is whether civilization can build the infrastructure needed to support it. This is the energy war behind AI. For decades, digital growth appeared almost magical. A new website could reach millions of users. A smartphone application could scale globally. Cloud computing allowed companies to expand without building massive physical infrastructure. But AI changes that equation completely. Unlike previous generations of software, artificial intelligence consumes enormous amounts of computing power. Training large models requires thousands of advanced processors operating continuously for weeks or even months. Running those models for billions of users requires even more infrastructure. This creates a fundamental shift. Digital growth is becoming a physical infrastructure challenge. Every AI request requires electricity. Every processor produces heat. Every data center requires cooling. Every cooling system requires water. Every watt of electricity must be generated somewhere and delivered through a physical network. The scale is staggering. Industry forecasts suggest future AI campuses may require multiple gigawatts of power. To put that into perspective, a single gigawatt can power hundreds of thousands of homes. AI is transforming energy demand from something incremental into something exponential. The chain now looks like this. Power generation feeds the grid. The grid feeds data centers. Data centers power AI compute. AI compute serves global users. For the first time in decades, the digital economy is colliding directly with the physical economy. The result is one of the largest infrastructure build-outs in modern history. The greatest challenge facing AI may not be processors, it may be the electrical grid. AI infrastructure can be planned, financed, and constructed within a few years. But the energy infrastructure needed to support it often takes much longer. Building a new data center may take months. Building a new transmission corridor may take a decade. Constructing new substations can require years of planning, permitting, and installation. Expanding regional grid capacity often involves complex engineering, environmental reviews, regulatory approvals, and major capital investments. This creates a dangerous mismatch. AI demand is accelerating rapidly. Grid infrastructure moves slowly. As more AI campuses connect to existing networks, pressure increases across transmission systems and substations. Bottlenecks begin to appear. Utilities face difficult decisions regarding capacity allocation. The challenge is not simply generating electricity. It is moving electricity where it is needed. Power must travel from nuclear plants, solar farms, wind facilities, and other generation sources through transmission networks before reaching AI campuses. Every step requires infrastructure. Every step requires investment. Every step requires time. This is why energy companies, utilities, governments, and technology firms are increasingly collaborating. They recognize a simple reality. The race to build AI is becoming a race to build infrastructure, and infrastructure cannot be scaled overnight. Electricity generation and electricity demand rarely occur at exactly the same time. The sun shines during the day, wind speeds fluctuate constantly, demand changes throughout every hour. AI systems, however, operate continuously. This is where energy storage becomes critical. Tesla Megapacks and other utility-scale battery systems are not power plants. They do not create electricity. Instead, they perform an equally important role. They store energy when supply exceeds demand and release that energy when demand exceeds supply. Think of batteries as the shock absorbers of the energy system. When renewable generation surges, batteries capture excess electricity. When demand spikes, batteries provide support. When grid disturbances occur, batteries help maintain stability. For AI infrastructure, this role becomes increasingly important. Data centers require reliable electricity every second of every day. Unexpected interruptions can disrupt operations, affect performance, and create financial losses. Battery systems help bridge those gaps. They improve reliability. They reduce peak demand pressures. They strengthen grid resilience. As AI expands, storage is becoming an essential layer between generation and consumption. The future energy system will not rely on a single technology. It will rely on multiple layers working together, and batteries are becoming one of the most important layers of all. When AI demand grows large enough, reliability becomes everything. That is why some of the world's largest technology companies are looking beyond intermittent energy sources and exploring long-term agreements with nuclear power providers. Nuclear power offers a unique advantage. It operates continuously, day and night, summer and winter, regardless of weather conditions. For companies operating massive AI infrastructure, this consistency is extremely valuable. A large AI campus may require electricity every second of every day, not occasionally, not when conditions are favorable, always. This reality is driving a renewed interest in nuclear energy. Long-term power purchase agreements can provide stable electricity supplies over decades rather than years. They reduce uncertainty, they improve planning, they support long-term infrastructure investments. The significance extends far beyond a single company. It signals a broader shift in thinking. Technology firms are no longer evaluating energy solely based on cost. They are evaluating reliability, scalability, and long-term security. The question is no longer simply how to power today's AI systems. The question is how to power the next generation of intelligence for decades to come. Nuclear power is increasingly becoming part of that answer. Even with reliable generation and strong transmission networks, energy systems still experience fluctuations. Demand rises, supply changes, weather impacts generation, unexpected events occur. Storage provides flexibility. Think of batteries as buying time for the grid. When generation exceeds demand, energy can be stored. When demand exceeds generation, that stored energy can be deployed. This balancing function becomes increasingly valuable as AI workloads grow. AI does not pause because the wind slows down. AI does not stop because clouds reduce solar output. Intelligence infrastructure expects continuous operation. Storage helps bridge those moments. It smooths variability. It reduces stress on generation assets. It enhances reliability throughout the system. In many ways, batteries act as a buffer between an unpredictable energy world and a predictable digital world. The larger AI becomes, the more important that buffer becomes. Storage alone will not solve every challenge, but without storage, future energy systems may struggle to meet the reliability expectations that advanced AI requires. Historically, electricity systems were relatively simple. Generate power, transmit power, distribute power, consume power. The AI era introduces a new layer, compute. Suddenly, energy systems are not merely delivering electricity to homes and factories, they are delivering electricity to intelligence. This creates an entirely new power stack. Generation remains essential, transmission remains essential, substations remain essential. Storage becomes increasingly important, and AI compute emerges as a major destination for electricity. Every layer depends on the others. Remove generation, and there is no energy. Remove transmission, and energy cannot move. Remove storage and flexibility disappears. Remove compute and intelligence cannot operate. This interconnected structure reveals something important. AI is not a standalone technology. It is part of a larger system. A system involving power plants, utilities, batteries, cooling infrastructure, water systems, semiconductor manufacturing, and global supply chains. Understanding AI requires understanding these relationships, because intelligence ultimately depends on infrastructure. And infrastructure depends on systems. What if electricity could be collected in space and delivered to Earth continuously? This idea may sound like science fiction, but researchers, governments, and private companies are actively exploring space-based solar power. The concept is straightforward. Solar arrays placed in orbit receive sunlight almost continuously. Without clouds, weather, or nighttime interruptions, energy production could occur around the clock. That energy could then be converted into microwave or laser transmissions and sent to receiving stations on Earth. If successful, the implications would be enormous. Continuous renewable energy, global coverage, potentially massive power generation capacity. For AI infrastructure, such systems could eventually provide another layer of energy security. Challenges remain significant. Launch costs, orbital deployment, wireless power transmission, efficiency losses, regulatory frameworks. Yet, history repeatedly shows that ambitious infrastructure projects often begin as impossible ideas. Railroads, satellites, the internet, spaceflight, space solar may represent another chapter in that story. The idea sounds futuristic, but so did many of the technologies that power modern civilization today. Generating electricity is only half the challenge. The other half is distribution. If future space solar systems become reality, a global orbital energy network may emerge. Instead of isolated power assets, multiple orbital platforms could operate together, delivering energy to receiving stations across different regions. Power could be directed where demand is highest. Energy shortages could potentially be addressed more rapidly. Critical infrastructure could receive support from multiple sources. This concept resembles an energy internet, a connected network capable of moving power across vast distances. Whether this vision becomes reality remains uncertain, but the underlying lesson is important. Every major technological breakthrough eventually creates new infrastructure requirements. Generating energy creates distribution challenges, distribution creates storage challenges, storage creates management challenges, systems evolve, complexity grows. New layers emerge. The future of energy may involve networks that extend far beyond the Earth's surface, and if that happens, AI may become one of the largest beneficiaries. We often discuss AI, energy, transportation, water, and infrastructure as separate industries. In reality, they are becoming one interconnected ecosystem. AI depends on electricity. Electricity depends on generation. Generation depends on water, materials, equipment, and supply chains. Every system influences every other system. This convergence is creating a new industrial era. An era where intelligence and infrastructure grow together. Future progress may be defined by how effectively societies integrate these systems. Reliable power, advanced storage, resilient grids, efficient cooling, sustainable water management, scalable compute infrastructure. These are not independent challenges, they are interconnected pieces of the same puzzle. The winners of the next century may not simply build better AI, they may build better systems. Systems capable of supporting intelligence at unprecedented scale. Systems designed for reliability, resilience, and abundance. Because intelligence alone is not enough. The infrastructure behind intelligence matters just as much. Most people see AI. Few see the systems behind it. They see a chatbot. They do not see the power plant. They see an AI response. They do not see the transmission network. They see intelligence. They do not see the water systems, substations, batteries, cooling infrastructure, industrial equipment, and engineering networks that make it possible. That is why understanding systems has become more valuable than ever. The future belongs to those who can see connections, who can understand dependencies, who can recognize how one technology affects another. At H2 Hub by Reni Energy, our mission is simple. Follow the system, explore the hidden infrastructure behind modern civilization. Understand power systems, discover water systems, learn how hydrogen networks operate. Investigate industrial facilities, analyze transportation infrastructure, study the machines that keep society running. Because the most important systems are often the ones people never notice. And the better we understand those systems, the better we can understand the future itself. The AI revolution is not just about intelligence. It is about energy, infrastructure, industry, civilization. Follow the system, understand the world, and discover the hidden networks powering the future.